The chilling final flight of Air India 171 left the aviation community and the public stunned. Everyone has been asking how one of the most modern and sophisticated airliners could crash in such a dramatic manner. The state-of-the-art Boeing 787 Dreamliner was introduced into airline service a decade and a half ago, and this was the type's first fatal crash. Oh, and that clock running at the bottom of the screen from the start of the video? It stopped now at about 40 seconds. That's the time the Air India pilots had after takeoff to realise there was a problem, figure out how to deal with it, and try to save their passengers and plane.
That's the real challenge with them. Their timeline was even shorter than Sully's ditch into the Hudson River. I think his was about 2.5 minutes. You go from climbing out on full power to no engines and you're a glider. The amazing part of that episode was that he worked through denial quickly and realized he wasn't going to make it to a concrete runway, and he had the Hudson River out in front of him. And so his decision process was decisive and it was quick. The Air India now a little bit different. It's basically a 60-second flight path straight off the runway. And if they lost power on both engines, all your options are taken away. You're along for the ride, and all you can do is kind of try to point the little bit of energy you have over the wings to get you to go one way or another. I think the captain did the best that he could given the situation he had. It was just total reaction on his part.
However, despite the headlines, commercial flying has never been safer. Over 4.5 billion passengers flew safely in 2024, and you're more likely to die in your bathtub than in an aeroplane crash. In the last 35 years, the chances of dying in an air accident have reduced dramatically. In 1990, it was 1 in a million. By 2025, it is now 1 in 15 million. That's probably why, when a headline reminds us that airliners still crash, it strikes a chord. Flying is a complicated amalgam of air crews, maintenance engineers, and air traffic control, not to mention the people designing and building the aircraft in the first place. But there is one constant.
I think there's always a human element, but I don't think it's always pilot error. Now, the human element might be something wasn't maintained properly, and it caused a problem. Years ago, we were taxiing out from Rome to come home, and we had an overheat in one of the engines, so we taxied back. They opened up the engine, and they found a lithium flashlight that had been left in the engine, and it was all melted and mangled. That wasn't the source of the overheat. It was just left there. So there are things that humans can do. They can make mistakes. They can leave things behind that may contribute to it. I'd be interested to see what the ratio is of pilot error, official pilot error, to mechanical error. My guess is it's pretty close to 50-50. The blame game goes both ways on things, but ultimately, when our NTSB comes out with their final report, they're pretty accurate about whether it was the pilots or it was just some sort of mechanical deficiency.
Every safety protocol we see today started with someone's worst day ever. In the 1930s and 40s, flying was a death-defying novelty. Engines failed. Airframes were torn apart. But each crash taught engineers to reinforce structures, add redundant systems, and improve materials. The 1934 TWA Fokker F-10 crash was caused by the structural failure of its wooden wingspan. This led plane makers around the world to switch to all-metal construction. But metal alone wasn't enough. With the world's first jetliner, the Comet, in 1952, came the first mystery crashes. The airliner was pressurized for passenger comfort, with the airframe flexing every time it flew to altitude. Engineers chased a ghost until they realized metal fatigue from square windows caused catastrophic cracks. Rounded windows, rigorous fatigue testing, and fail-safe structural design became standard. In 1956, in the skies above the Grand Canyon, two planes that had recently taken off from Los Angeles International Airport collided. All 128 passengers and crew aboard the United Airlines DC-7 and the TWA Constellation were killed.
If you're an AI enthusiast, you need to get in on this. Chat LLM Teams brings all your favorite AI models together in one easy-to-access platform. Use GPT 4.1, Gemini 2.5 Pro, DeepSeek, and even open-source LLMs, all from a single platform. Video and image generator features are also included, like DAL-E, Flux, Hailuo, Luma, and more. Root LLM will automatically pick the best model to handle the task. Need to avoid AI detection tools? Humanize will rephrase whatever you've generated, making sure it doesn't sound like something by AI. Are you a coder? Code LLM is a VS Code-based editor that can answer questions about your own work or generate it for you. For non-coders that still need the work of one, Deep Agent's got you. It can build you a website or app with a simple prompt. All this for an affordable $10 per month. That's cheaper than paying for all the LLMs separately. Check out chatllm.abacus.ai or click the link in the description.
The accident spurred a $250 million upgrade to the air traffic control system, a significant investment in those days. It also led to the establishment of what is now the Federal Aviation Administration to oversee air safety. The deadliest air crash in history wasn't a system failure. It was fog, miscommunication, and cockpit confusion. Two fully laden Boeing 747s collided on the runway at Tenerife, killing more than 508 people. After Tenerife, Crew Resource Management, or CRM, was born, redefining pilot teamwork and communication. Unseen weather can also have a devastating effect. L-1011 landing at Dallas-Fort Worth in a thunderstorm experienced, at the time, one of the least understood weather phenomena, wind shear. At 800 feet, the plane was hit by a microburst, a strong downward draft, and a direction change in the wind. The plane dramatically lost speed and fell from the sky a mile short of the runway. 134 of the 163 people on board were killed. This triggered 7 years of research by NASA and the FAA, leading to the introduction of onboard forward-facing wind shear detection radar. It became standard equipment on airliners in the mid-90s. Since then, there has only been one other wind shear-related accident. In 1996, when a TWA 747 from New York bound for Paris blew up mid-air off the coast of New England, the first thought was terrorism. However, a painstaking investigation of the crash revealed that fumes in the empty center fuel tank of the plane had exploded due to faulty wiring. Subsequently, aircraft manufacturers have improved the insulation on wiring and introduced systems to flood empty fuel tanks with inert gas, making them no longer a hazard. Shawn Pruchnicki is ex-accident investigator, pilot, and now assistant professor at Ohio State University.
If you go back to the 40s, 50s, and 60s, it was mechanical issues, primarily engines. And it was quite common with these 4-engine airplanes for these airplanes to land with an engine shut down. I don't want to say that was absolutely the norm. I mean, it wasn't every flight, but it by no means was rare for that to happen. And then sometimes there were other issues, and that resulted in accidents. If you look back at those accidents, it was quite frequently mechanical failures. Whereas now, that is not the problems that we have. Typically, are mechanical failures. It is just, quite frankly, the complexity of these machines.
The airliner you fly these days is part jet, part data center, and part software lab. Modern aircraft have 3 system layers. There is the structure of the airframe and engines, the hydraulics and electrical systems. Additionally, there are avionics and software required to operate it. In some respects, the airplane you travel in today is no more than a flying computer. An Airbus A350 has over 10 million lines of code. The sensors, actuators, and flight management computers must talk flawlessly to one another, or chaos ensues. Tragedy struck when the single angle of attack sensor failed, feeding incorrect data to the 737 MAX MCAS system. In 2 deadly incidents, it repeatedly forced the nose down. The pilots fought hard, but lacked proper training and documentation to quickly understand the situation and avert disaster. Boeing eventually redesigned MCAS and improved training protocols.
Accidents are multifactorial. It's always a combination of things. Almost exclusively, the types of accidents that we see are automation-related accidents. That's where my area of work comes in, is understanding the interface between automation and humans. and the confusion that takes place at this interface. In other words, the humans understanding what the automation is doing, automation doing things that sometimes it's not always programmed to do. In fact, the MAX accidents are a perfect example of that. And Asiana in San Francisco is another example of that. And we could go on and on. But I would say that that is the primary area with the types of accidents we've seen over the last several decades.
There are instances where, like the mechanical parts of an aircraft, software also wears out. Sometimes it's not apparent what the software controlling the plane is doing. Shawn Pruchnicki is researching software certification for the FAA.
We came across an accident that happened off the coast of Australia, I believe. This individual event was an Airbus product where the airplane started pitching nose up and nose down violently. And what they ended up finding was some of the code ended up going bad, that it didn't necessarily rewrite itself, but it ended up deteriorating. And the airplane ended up, of course, using that code. And now the code was invalid and the airplane started reacting to that code. That software was fine originally, but to make it sound extremely simple, the ones and the O's got mixed. And we all know that, software, can do this, right? And this happened in this event. And it was very serious. A lot of people were hurt on this, like some quite seriously, by this airplane violently pitching up and down.
Software bugs alone aren't enough to ground a plane. Maintenance and human factors complete the picture. Even minor maintenance missteps, such as a wrongly installed component, can trigger a chain of events. And in aviation, chains break catastrophically. Every bolt and bearing passes through human hands. Maintenance manuals run to thousands of pages. Skipping a lubrication step or misreading a schematic can set off a chain reaction. For decades, improper maintenance of aircraft mechanical systems has been a contributing factor to aircraft accidents. An incorrect repair to China Airlines jumbo jet led to its breaking up mid-air in 2002. The plane had previously been involved in a tail strike, where the lower tail fuselage hit the runway on takeoff. The investigation revealed that the repair was insufficient to maintain the structural stability of the airframe. It resulted in the deaths of all 225 people on board. However, the avionics and software that fly a plane have become even more crucial to its safety.
The mechanics have come such a long way from, where they were many, many decades ago, where the airplanes were a lot more simple to fix and to learn how to fix. Now they are much more complicated. I mean, just even the engines themselves, I have mechanics tell me, are extremely complex and complicated to fix, and the tolerances are unbelievably tight. And in the airlines and the third-party companies that sometimes airlines outsource maintenance to understand this, the importance of proper maintenance and how difficult it can be to understand these machines is absolutely tremendous.
In commercial flying, the buck stops in the two front seats. Early pilots received on-the-job training through actual flights. Today, crews log hundreds of hours in simulators that replicate engine failures, stalls, and weather crises, down to turbulence models and real-world airports. In commercial aviation, it's almost universal that pilots do the takeoffs and landings, and the bit in between is completely automated. So, is the automation doing away with airmanship?
Well, I think that's been a debate for some time now. As we're getting more and more into the 21st century, there's more automation on airplanes. And it makes it for a better ride, it makes them more reliable, it makes them safer for sure. But the downside of that is, do the airmen have the same skills that they used to have? When you think about the modern era of flying, it was basically World War II, Korean War, maybe Vietnam War pilots that were coming out of that. That was all stick and rudder flying. Those guys and gals were very good at that part of it. Now, as we get into the 21st century, there's more button pushing and dialing of things than there ever were before. The training has improved though. And so when I go to training, we hand fly a lot of the flight. In fact, they force you to turn off the autopilot and hand fly the airplane even though in the real airplane, you might keep the autopilot on. So that's to keep your skills sharp. The first hour or so in the simulator, they just tell you, let's go fly around. I don't ever do that in the airplane because passengers want to get from point A to point B, but it's nice because it keeps my skills sharp. So yeah, there's been a definite trade-off in that over the years.
It takes 10,000 hours to master flying, but only 10 seconds to face life or death decisions. However, pressure, fatigue, or unfamiliar controls can cloud judgment. In the tragic case of Air France 447, a sensor iced over, causing the plane to crash. The autopilot disengaged. Confused by false speed readings, the pilot pulled up, stalling the aircraft from 38,000 feet. Sadly, everyone on board the Airbus 330 died as it plunged into the depths of the South Atlantic. Training isn't just about flying the plane. It's about diagnosing the unknown in seconds, often with outdated or contradictory information. Or in some cases, no accurate information at all.
Look all the way back at the Turkish accident in Amsterdam, in Schiphol. The crew had no idea that the autothrottles were tied to the radar altimeter. When the radar altimeter failed, the autothrottles said, because it went to zero, said, oh, well, we're on the ground. So it pulled the thrust all the way back. Well, they were on short final, still several hundred feet above the air. So the pilots are looking out the window, looking for the lights because it was low visibility, so they could make the call, landing, or do a go around. And the autothrottles are pulling the thrust back. And then all of a sudden they realize they're getting slow and there's no thrust. They have no idea why the thrust levers just came back or why that would happen. They grab the thrust levers, they shove them forward, but it takes time for the engines to spool up and start producing thrust. There just wasn't enough time.
As the number of planes flying has increased, so has the complexity of air traffic control. And with more people wanting to fly, the airspace gets more crowded, particularly around popular destination airports. The Midair Collision in January 2025 over the Potomac River in Washington, D.C. highlighted the issues faced by air traffic controllers.
Certainly here in the States, we have a serious problem with air traffic control concerns. We're very short-staffed, right? And the primary problem there is runway incursions because of the way that the radio systems are designed, that we have miscommunications that aren't always caught. Sometimes pilots reading back the wrong thing and controllers not catching it. Pilots are sometimes pulling out on the runway when they're not told to because they're not hearing the right thing. So then we're having near misses. And a lot of that is related to the controller shortage because they're tired. They're working 6-day weeks, they're working forced overtime. And this is a job where you can't work that job tired. That's going to catch up with you. And these little mistakes are going to start slipping through.
However, air traffic control accidents have had long-term positive effects on the safety of all those flying today.
Years ago, there was an airliner that crashed into a mountain down in Colombia. They were on a particular route that they were supposed to fly, and air traffic control gave them a shortcut. Well, that shortcut just happened to be right through a mountain. The lack of coordination between the pilot and the first officer, the captain, the first officer. And so all of those little things that contributed to that mishap are things that we've folded into the training in the future. And the technology side of it was they brought along a thing called EGPWS. It's electronic ground proximity warning systems, so that if you do get close to rocks, it will squawk at you and tell you to pull up. So instead of flying right into what we call lumpy clouds, which is bad, you get a warning ahead of time and you can climb or turn. So all of that stuff is things that came out of a particular accident.
One aspect of commercial flying that we touched on earlier is CRM, or crew resource management. What we have seen is that if a problem arises in the cockpit, the pilots have maybe seconds to react, so trust between the two is imperative. All major airlines have adopted this practice to ensure that pilots work together as smoothly and efficiently as possible.
The first officers have a list that they can put employee numbers on called a do not pair with list. So if they fly with a captain that they don't want to fly with again, maybe there's a personality conflict, maybe for whatever reason, they can put up to 3 captains on their list. The captains don't have the same luxury. For me, I have to work with everybody. But again, we've got a professional standards department, and I should apply some leadership and say, hey, let's be professional today. Let's not talk about politics. Let's not talk about something angsty. I usually will try to put my crew at ease. Bad dad jokes are good for that. If we can all laugh with each other before we take to the air, that's good. We feel good about one another, but we stick to the book. We stick to standard operating procedures. We do things the way we're trained. All of that is very helpful.
As we have said, there is always a human factor in every aircraft accident. Over the years, training and automation have significantly reduced the likelihood of human error. But could AI be the answer? Could AI fly a plane better than a human pilot and make air travel risk-free?
Could we sit here and dissect all of the different problems, and maybe there's some low-level information that AI could provide? Yeah, maybe that's possible. But as far as being a major player in decision-making and a major support tool, no, AI is nowhere near that, nor is it nowhere near that on the flight deck.
A typical crash isn't the result of one glaring error, it's a cascade. One faulty sensor, a tired crew, a storm cell was not noticed in time, a miscommunication with ATC. When the holes in every layer of defense align, that's when disaster happens. However, every crash changes the blueprint. Each crash is studied in microscopic detail. Wreckage is reconstructed, simulations are run, and the lessons become new operating procedures and regulations. But here's the miracle. Even with over 100,000 flights daily, crashes are vanishingly rare. Because the system learns.
Remember to hit the subscribe button and ring that bell to stay updated with our latest content. And while you're here, why not check out another one of our exciting videos? Thanks for watching, and see you in the next one.